let's start it. As part of Hadoop Foundation, first we are going to discuss Hadoop Introduction. What is Hadoop? What is Hadoop? Hadoop is a big data framework team. Hadoop is a big data framework. Big data framework. Big data framework. It has storage. It has storage and processing. Hadoop has both storage and processing team. Storage we use HDFS file system. HDFS file system. Processing we have MapReduce, Pig, Hive, etc. There are other frameworks. So Hadoop is a big data framework. It has both storage and processing. Storage we use HDFS file system. Processing we have different frameworks, MapReduce, Pig, Hive, etc. We will discuss what are different Hadoop frameworks. Okay. Next one, Hadoop is implemented using Java language. Hadoop is implemented using Java language team. Hadoop is implemented by duck cutting. Vendor of Hadoop is Apache. Vendor of Hadoop is Apache team. Apache Friends or Apache Foundation. So Apache maintains all open sources. So Hadoop is a open source. Hadoop is a open source and free. No need to pay any license cost. It is completely free. Open source means they give complete source code thing. They give complete source code. Understand, right? Now let's understand what is big data. What is big data? What is big data? What is big data? Big data means huge volumes of data. Huge volumes of data which cannot be stored and processed, using traditional technologies. Using traditional technologies like RDBMS and application programmings within short time. Yep. So big data means huge volumes of data which cannot be stored and processed using traditional technologies like RDBMS and application programming within short time. Because most of RDBMS has a limitation. RDBMS does not support unlimited storage. First reason, RDBMS does not support unlimited storage RDBMS is a RDBMS. Most of RDBMS or RDBMS file system is not a distributed file system. Is not distributed file system. Distributed file system. So because of all these reasons, these are not supporting unlimited storage and these are not supporting parallel processing. Most of RDBMSs are not supporting parallel processing team. So big data means it's a huge volumes of data which cannot be stored, which cannot be processed using these RDBMS and application programmings within short time, fast, because cluster has a limitation. RDBMS cluster has a limitation, and it is not a distributed file system. Okay. So now let's understand classification of big data type. Classification of big data. So big data can be classified into three categories. Big data can be classified into three categories. Big data can be classified into three categories. Three categories. They are first one, structured data. Structured data. So both Hadoop and RDBMS supports structured data. Second one, semi-structured data. Semi-structured data. Hadoop supports semi-structured data. Most of RDBMS not supports. Most of RDBMS not supports semi-structured data. Third one, unstructured data. Unstructured data type. Hadoop supports unstructured data. Most of RDBMS not supports unstructured data type. Let's understand structured data. Structured data. Can anyone tell me what is structured data? So structured data means the data does have a proper format. Yes or no? Data has a proper format. Yes. So data has a proper format associated with it. Proper format associated it. Example, tables. So tables first we create a table structure. Then we will insert data. In table, data presented in rows and columns format. Yes or no? So data associated with the structure. So what is each column type? Yes or no? So structured data means data has a proper format associated with it. Example, tables. So RDBMS, Hadoop supports RDBMS and Hadoop supports structured data. Structured data. Next, coming to semi-structured data. Tell me what is semi-structured data? So data does not have a proper format associated with it. Data does not have proper format, does not have proper format associated with it. Associated with it. Example, XML, JSON, CSV, etc. These are semi-structured data. So proper format not associated with these kind of data type. Coming to unstructured data. Data does, here most of RDBMS not supports, most of RDBMS not supports semi-structured data, but Hadoop supports semi-structured data type. And unstructured data does not have any format. Data does not have any format associated with it. Example, log files. There is no proper format or any format associated with log files. Charting data, reviews data, videos, audios, images, etc. So this data, there is no proper format, any format associated with this data type. Yes, sir. So Hadoop, most of RDBMS not supports unstructured data, but Hadoop supports unstructured data type. Unstructured data. In RDBMS, we have a concept called blob. In a particular column, we can define a blob. We can store the data, but problem is doing analytics is very difficult to do. Doing analytics on that unstructured data is very difficult in RDBMS. So Hadoop supports both structured data, semi-structured data, unstructured data type. And next very important point of big data is characteristics of big data. Characteristics of big data. There are many characteristics, but there are mainly three characteristics. There are mainly three characteristics. They are one, volume, two, velocity, third one, variety. So there are many characteristics. See, mainly three characteristics: volume, velocity, and variety. Volume means huge volumes of data. Hadoop supports unlimited data type. Hadoop supports unlimited data. Hadoop supports unlimited data. Hadoop supports unlimited data type. Unlimited data. There is no limit in Hadoop cluster size. There is no There is no limit in Hadoop cluster. Hadoop cluster, you can add n number of missions. RDBMS does not support. RDBMS does not support unlimited storage. Does not support unlimited storage. Unlimited storage because there is a limit. There is a limit in RDBMS cluster. RDBMS cluster. Yep, there is a limitation in RDBMS cluster because RDBMS does not support unlimited missions in a cluster. So that's why RDBMS does not support unlimited storage. Now coming to velocity. Velocity. How much speed data is growing is called velocity. How much speed data is growing, how much speed data is growing is called velocity. Example, Facebook generating, yep, Facebook generating 200 TB data every day. 200 TB data every day, team. YouTube, every hour, YouTube around 48 hours video is uploading. In YouTube, each minute, 48 hours video is uploading. Twitter generating 400 millions of data, many millions of data. So Twitter processing 400 millions tweets. 400 millions tweets. So lot of social media generating data. Social media generating lot of data. Facebook, YouTube, many social media sites generating huge volumes of data. To store such kind of data, there is no other framework. We have only Hadoop. Okay, coming to variety of data. Variety means structured, semi-structured, and unstructured. Hadoop supports all kinds of data. Hadoop supports all kinds of data. RDBMS not supports. RDBMS supports only structured data. Hadoop supports all kinds of data. Yep. Challenges associated with big data. Challenges associated with big data. So first challenge, storage team. First challenge is storage. Storage. There is no, before big data, there is no technology. There is no technology which stores huge unlimited data. Which stores unlimited data. Unlimited data. First challenge is there is no technology which stores unlimited data. Second challenge, processing. Processing. There is no application programming. There is no application programming which can process huge volumes of data very faster. Which can process huge volumes of data. Huge volumes of data in very short time. Very short time or faster. There is no application programming which can process huge volumes of data very faster. So these are two challenges associated with big data team. Hadoop resolved these two problems. First one, Hadoop solved big data problems. Big data problems using HDFS and MapReduce using HDFS and MapReduce team. HDFS stores unlimited storage. HDFS stores unlimited storage. HDFS stores unlimited storage. Unlimited storage. There is no limit in HDFS file system. There is no limit in HDFS file system. Yep. So HDFS stores unlimited storage. It stores unlimited storage, and there is no limit in HDFS file system. It is a distributed file system. Distributed file system. It is a distributed file system thing. Coming to MapReduce. MapReduce is a algorithm. We can implement MapReduce with Java or Python. It supports plenty languages. MapReduce supports plenty languages. MapReduce is a parallel processing architecture thing. MapReduce is a parallel processing architecture. So it processes data parallelly so that you get a response very faster. First one, HDFS is a distributed file system. Whenever you store data into HDFS file system, it will split the data into multiple blocks. It stores each block into different mission. So whenever you submit MapReduce application to Hadoop cluster, Hadoop can process MapReduce application parallelly. There is no existed technology before big data team. First of all, RDBMS is not a distributed system. So parallel processing not happens. So if you want to process parallelly, you have to get the data into application location and you have to write manual parallel processing applications. But MapReduce is a algorithm. It is a parallel processing algorithm. Data already distributed. Data already distributed. Distributed means whenever you store data into HDFS file system, it will split the data into multiple parts. Each part to store in different mission. Your data going to store in different missions. We call this process is distributed data. So data is going to divide into multiple blocks. What is block? How it is going to divide? What is the factor it uses for dividing the data? We are going to discuss everything in HDFS file system. Okay. So MapReduce is a parallel processing architecture. So it can process data very faster. Let's say diagrammatically. Let's see RDBMS and Hadoop. This is my RDBMS and this is my Hadoop. Here I have one master. Let's say we have one master and we have multiple worker missions. Multiple worker missions. Let's diagrammatically discuss it so that it will clear all your doubts. So we have 5 worker missions. 5 worker missions. 1 master mission. Master and workers. Workers are slaves. So workers stores the data too. Okay. So same architecture we have in Hadoop. Let's say same architecture we have in Hadoop side also. Assume client want to place data. This is client mission. Client mission. Client want to store the data. Let's say data is file 1, size is 300 MB. File name is file 1, size is 300 MB. 300 MB. So client send a request to master mission. A master mission, I want to store file 1. I want to store file 1. Then master mission finds free slave mission to store the data. So file stores the data too. So first here RDBMS master finds free slave mission, and here it will store entire. Let's say first mission accepted request. It will store 300 MB data into single mission. 300 data into single mission. Coming to Hadoop, here also client want to store file. So file size is 300 MB. File size is 300 MB. File size is 300 MB. File name is F1 and file size is 300 MB. 300 MB. So client want to store this 300 MB file data. Client to send a request to master mission. A master, I want to store file. File name is F1. File name is F1. File size is 300 MB. Then here client will prepare metadata. Client will prepare metadata. Before storing the data, it will prepare metadata. Metadata. In this metadata, it will contain information of file to block, block to data nodes list 1, 3, 5. Let's say file 1, block 2, 2, 3, 5. File 1, block 2, block 3, 3, 4, 5. Let's say it assigns in this way. Default block size is 128 MB. 128 MB. Default replication is 3. Default replication is 3. For high availability, it will store multiple duplicate copies of each block thing. So first block 1 stores here. Block 1 creates here. Block 1 creates here. Yep. So default replication is 3. It will create 3 replicas for block 1. This is block 1 and block 1. Block 1. Okay, similar way, block 2 placed in 2, 3, 5, 2, 3, and 5. So this is block 2, block 2. So block 2 and block 2, block 2. So same way it will create one more block, block 3 in the third mission, okay, and fourth mission and fifth mission. So block 3, and block 3 and block 3. So in this way it will place them. So we have 3 blocks. So 300 MB data divided into 128 MB. So we got 3 blocks. So each block size is 128 MB. So first block 1 is 128 MB. Block 2 is 128 MB. Block 3 is 128 MB. 128 MB. Okay, sorry, 44 MB. 44 MB. Remaining space of block 3 is 44 MB. So it is placed block 1, block 2, block 3 in different mission stream. Whenever user wants to read data, user requested to read, then this request comes to master request to read file 1. Request to read file 1. Then master identifies where is file 1. How many missions involve in RDBMS? Only one mission involves to process your data. This is 300 MB. You will get very faster. Here, how many missions involves to process in Hadoop side? So same request is came, read request, read file 1, request came. When read request to file 1, then when it comes to master mission receives this read request file, may be MapReduce, may be Pig, may be other processing framework. It will start MapReduce instance here. It will start MapReduce instance here. So 3 processes parallelly process your data type. 3 MapReduce instances process your data request, data read request. Here only one mission involves to process. Here only one mission is involving to process your data. Here 3 missions are involving to process the data. So compared to RDBMS, Hadoop process your data very faster. Understand, right? What is distributed data? How it process parallel processing? So whatever the issues associated with big data or challenges associated with big data, Hadoop resolved using HDFS file system using MapReduce mechanism. MapReduce is a parallel processing mechanism. HDFS is a distributed storage type. Distributed storage. It can support unlimited data. Unlimited data. You can store any size of data because here coming to here number of missions is limit. Maximum we can store 256 missions in a cluster. Maximum we can store 256 missions in a cluster. The popular database called Oracle. In Oracle, we can take maximum of 256 missions. But here, there is no limit. You can take n number of missions. N number of missions. There is no limit. There is no limit. There is no limit. You can take n number of missions. You can take n number of missions. There is no limit to it. There is no limit. You can take n number of missions. N number of missions. That's why we are saying unlimited storage. Hadoop supports unlimited storage. Yeah. So today we are going to discuss different vendors of Hadoop. So first, Apache Hadoop is a open source. Apache Hadoop is a open source and free. Open source and free. Open source means they give complete source code. Open source means they give complete source code. So I said Apache Hadoop is implemented using Java. Hadoop is implemented using Java. So they give complete Java coding. They give complete Java code. So based on this open source, based on this open source, many vendors implemented Hadoop, and they are providing enterprise versions. So example, we have different vendors of Hadoop is. So we have first one Cloudera providing CDH, Cloudera distribution Hadoop. Next one, second one, Hortonworks providing HDP platform. So HDP stands for Hadoop or Hortonworks distributed platform. And next one, third important vendor is Mapper providing Mapper Hadoop. And similar to Mapper, we have another vendor, Amazon Amazon giving EMR. EMR stands for Elastic MapReduce. And similar to these vendors, we have one more, IBM. IBM providing InfoSphere. We call it as Big Insights. And other popular vendor is Microsoft. Microsoft providing HD Insights. HD Insights. There are other vendors. These are popular vendors too. These are popular vendors in the market. Cloudera providing CDH, Artenworks providing HTTP, Mapper providing Mapper Hadoop. Along with Apache, we are having these vendors Hadoop team. But all these vendors backend is Apache Hadoop only. So all these vendors implemented Apache Hadoop based on Apache Hadoop open source team. So whatever the commands we execute in Apache Hadoop, same commands will work in all the vendors. There is no difference. There is no difference for vendor to vendor. The commands, program submission, program execution is same in all vendors. Different vendors are providing different user interfaces, graphical user interfaces. Cloudera providing different user interface, Hortonworks providing different user interface, Mapper providing different user interface, Amazon providing different user interface, and additionally they are providing admin interfaces also. Cloudera provides Cloudera Manager, Hortonworks, Apache, Mapper, these people uses Apache Ambari for administration purpose. And additionally, along with Hadoop, additionally they are providing additional features like Cloudera providing GUI user interface. So Impala, and later they donated to Apache. Okay, so mainly all these vendors follows Apache Hadoop team. If you practice on Apache Hadoop, working on these vendors is same thing. There is no difference. There is no difference too. And recently Cloudera and Hortonworks merged. So earlier, these two people are major competitors in the Hadoop world. Cloudera and Hortonworks, these people are major competitors. And recently, these two people are merged. So we are getting only one product. From Cloudera, they are releasing different products too. Both people are merged. Okay. Now let's understand features of Hadoop. First one, cost effective. Cost effectivity. First important feature is cost effective. Hadoop software is free. Hadoop software is free. RDBMS software, let's say RDBMS, most of RDBMS are not free. Most of RDBMS are not free. Hadoop RDBMS cost is high. Let's take Oracle. Oracle cost is very high. Yes or no? Hadoop software is free. No need to pay single rupee. Next one, Hadoop works on commodity hardware. So commodity hardware means PC less than commodity hardware. commodity hardware less than server hardware, or high-end hardware, high-end hardware or certified hardware, certified hardware. So commodity hardware is less than server hardware. Cost is very less compared to server hardware. We can buy multiple machines of commodity hardware instead of purchasing single server hardware. So RDBMS, let's say Oracle. Oracle software is very high, and every year we have to renewal. And Oracle not works on all hardwares. Means I'm not saying development server, production servers, live servers. If you want to make your server 24/7 up and run, you need to use Oracle certified hardware only. Then only they give 100% reliability. If you use normal hardware, chances of failure of your hardware is very high. That's why they cannot give 100% reliability. But Hadoop supports normal hardware too. Normal hardware called commodity hardware. It does not require any specialized hardware. It does not require any certified hardware. Next important feature, large cluster of nodes, large cluster of nodes. So there is no limit in Hadoop cluster team. There is no limit. You can take any number of machines, RDBMS has a limitation, limitation in cluster. RDBMS has a limitation in cluster because RDBMS depends upon the operating system. Operating system has a limitation. That's why RDBMS has a limitation. But Hadoop, there is no limitation. There is no limitation. We can take n number of machines. We can take n number of machines team. N number of machines in Hadoop cluster. We can take n number of machines in Hadoop cluster. There is no limit. You can take n number of machines in Hadoop cluster. So there is no limit in Hadoop cluster size. Next one, parallel processing. Before that, let's understand Hadoop is a distributed storage. Distributed storage or distributed data. Hadoop is a distributed data. Hadoop uses HDFS file system team. Hadoop uses HDFS file system. Hadoop uses HDFS file system. It is a distributed file system. It is a distributed file system. It is a distributed file system team. Example, let me take cluster. So we have a Hadoop cluster, one master and multiple slave machines. Team. This is my cluster. So you can take n number of machines in Hadoop cluster. There is no limit. You can take n number of missions. So whenever any client want to store the data, whenever any client want to store the data, so first client approaches master mission. Client approaches master mission. Let's say this is 300 MB. 300 MB. So here, first client approaches with master mission. Client approaches with master mission. Client prepares metadata. Sorry, master prepares metadata. Master prepares metadata. Okay. Then returns this metadata information back to client. Once a client gets metadata, client performs writing. Master will not write it. Master will not write. Master prepares metadata and gives information to client. Then client is responsible to write the data. This process we call HDFS write flow. We will discuss in HDFS concept what is HDFS write flow, what will happen in HDFS write flow. Okay. So client is responsible to write the data type. Master just prepares the data, prepares metadata and returns that metadata information back to client. Okay. So here client writes data into cluster. Your data is going to split into multiple blocks. Your data is going to split into multiple blocks and stores into Hadoop cluster. So in HDFS file system, data divided into multiple blocks. Data divided into multiple blocks. And each block placed in different mission. So that's why we are calling it is a distributed it data. HDFS file system is a distributed file system. Hadoop distributed file system. Okay. Now let's understand. So here user placed data into missions. It is prepared metadata in this way. Let's say file 1, block 1, it is placed 1, 3, 6. File 2, file 1, block 2, 2, 4, 6. Here 1, 3, 5. Next one, file 1, block 3, 3, 5, 6 or 7. Okay. So here it places block 1 here, block 1 here, and block 1 here. Block 1, block 1, block 1, and next one block 2 placed in 2, 4, 6. Block 2, block 2, block 2. Next one, block 3 placed in 3, 5, and 7. So block 3 placed in third mission and fifth mission and seventh mission. Okay, so data is distributed. Now very important feature is fourth important feature, parallel processing. Hadoop is a parallel processing. Parallel processing framework. Hadoop is a parallel processing framework. So to process parallel, we use MapReduce, we use Pig, we use Hive, etc. processing frameworks. We use etc. processing frameworks. Okay. So these are different parallel processing frameworks. Hadoop process data parallelly. Hadoop process data parallelly. Let's say team, user submitted MapReduce request. Let's assume this is MapReduce program. Let's say MapReduce program. User requested, this is client mission. Let's say client 2. This is client 1. Client. This is another client. This is another client. This client want to process file 1. Then requested master. Client requested master. Master, I want to process file 1. Then master finds file system with blocks information, gives file system. Then based on the sorting order, 1, 2, 3. Then based on the sorting order, MapReduce instance is created here. MapReduce instance is created here. And MapReduce instance is created here. So first mission processing block 1, second mission processing block 2, third mission processing block 3 parallelly. So you get response very faster. MapReduce is a parallel processing. So Hadoop is a parallel processing. It processes data parallelly. It will create a MapReduce or any big data processing algorithm parallelly, so that you get responses very faster team. Understand, right? So Hadoop is a parallel processing mechanism. It processes data parallelly. There are many big data processing frameworks, MapReduce, Pig, Hive, Spark, etc. There are other frameworks also. So these all frameworks are parallel processing frameworks. Once you submit a request to Hadoop, Hadoop starts your process in multiple missions. Wherever data is presented, it will start parallel processing, so that you get a response very faster. Okay. Next important one team, very important one, automatic failover management. Automatic failover management. Automatic failover management. Automatic failover management. Very important feature team. I said one important point here, in cost effective, Hadoop is a free, software wise, no need to pay single rupee. You can install Apache Hadoop, you can download and you can install Apache Hadoop. If you want to customize, it is open source, you can customize. And it does not require any specialized hardware. It can work on any hardware, commodity hardware. So if it is a commodity hardware, chances of failure is compared to certified hardware is high. Yes or no? Compared to certified hardware, commodity hardware failure is high. That's why it maintain multiple replicas. To resolve fail automatic failover, automatic failover, or fault tolerance, tolerance. Hadoop maintains 3 replicas of each block. 3 replicas of 3 replicas of each block. So this is default. We can increase or we can decrease. Let's say we are using certified hardware, then no need of 3 replicas, maintain 2. So this replicas we can increase, we can decrease them. So by default to 3 replicas, you can increase or decrease. If one mission fail, still we can access from other mission, because same block is presented in other missions also. Yes or no? Assume this mission is failed. This mission is failed. Where is block 1 and block 3? Block 1 is presented here. Block 1 is presented here. Where is block 3? Block 3 presented here. Block 3 presented here. Yes or no? Still we can access file system data. That is the main purpose of replica stream. Replica means duplicate copy of a block. So by default it will maintain 3 replicas of each block. So if one system fail, still we can access. In cluster, if any mission fail, still we can access. HDFS file system, because we have duplicate copies of blocks in other missions. Main important point to team, it will not place all duplicate copies in same mission. Let's say block 1 contains 3 duplicate copies. First mission, third mission, fifth mission. Instead of that, it will not place in same mission. In Hadoop cluster architecture, I will give clear idea team. Okay. Yep. So next very important feature. Is data locality optimization. Very important feature. Data locality optimization. What is data locality optimization? Let's see team. Let's see. So this is my traditional architecture. And Hadoop architecture. Traditional architecture and Hadoop architecture. We have a database. In traditional architecture, we have a database. Any RDBMS database. And we have application. This application may be Java application, may be Python application, may be Scala application, may be any application too. It may be any application. First we send request to database. database. Assume here we have a data. Let's say this is sales data. Sales data. Assume this is 10 GB data. 10 GB data. So here this 10 GB data moves from database location to application location. Yes or no? This 10 GB data moves to application location. Here we apply processing. Here we apply processing. This data moves from database location to application location. Here we apply processing. But coming to RDBM, Hadoop cluster. Hadoop cluster, let's say we have multiple missions. We have multiple missions. Data presented in different missions. Okay, let's say we have 4 missions. In this cluster, we have 4 missions. So user submitted MapReduce request. User submitted MapReduce request. MR request. Assume block 1 of file. Presented in 1 mission, 3rd mission, and 4th mission. Let's say here this is block 1, block 2, block 3. Assume we have 3 blocks of file. So whenever user submitted this request, first client gets information from master mission. Then this MapReduce instance is created in mission 1. Block MapReduce instance is created in mission 2. MapReduce instance is created in mission 3. This one process this block parallelly. This one process this block parallelly. This one process this block parallelly. Understand, right? MapReduce instance is created in data missions, not in application location, not in client mission. Data not moves to application location. Application moves to data location. Legacy architecture, data moves to application location, but in Hadoop architecture, application moves to data location. Application instance is created in data location. So data locality optimization means application instances are creates in data location. Data not moves to application location. Data not moves to application location. Application instances are created in application instances are created in data location. So data size may be any size. Parallel processing. MapReduce works parallelly. MapReduce instance is created in multiple missions. So performance is very faster compared to other technologies. So other technology here, how many missions are involved in? One mission involves in processing, but here multiple missions involves to processing. Performance wise very faster. response is very faster. Okay, so let's say we have a 10 GB, 10 GB by 256. Many missions involves to process your data request. Okay, so see, data size is huge here. Data size is huge. Yes or no? What is the size of your application? Maximum application size is KBs. Max application. If it is max, MBs file. MBs. Yes or no? How many instructions we write? Maybe thousands of instructions. What is the size of those thousands of instruction size? Maximum is MBs only. Yes or no? So instead of moving MBs instructions into data location, in traditional applications, data, GBs, TBs, petabytes of data we are moving to application location. It is not good practice. But in Hadoop, only application is moving to data location. So we send a request to MapReduce request to master mission, and master mission gives information of where is file blocks. Then client creates instances of your MapReduce applications in a data location. Okay, so understand, right? The data locality optimization. So next, very important feature team, heterogeneous cluster. Heterogeneous cluster, very important feature. Heterogeneous cluster. Heterogeneous cluster. Let's understand him diagrammatically. Let's understand. We have a master. We have different worker missions. Different worker missions. We have different worker missions. We have different worker missions. Let's say team, this is my master mission, and these are workers. Master mission, I'm using Oracle Enterprise Linux, Oracle Enterprise Linux, and Oracle hardware, Oracle Enterprise Linux, Oracle hardware. So we are using Oracle Enterprise Linux. Operating system is Oracle Enterprise Linux. Hardware is Oracle hardware. Coming to worker one mission, operating system I'm using IBM AX. Hardware I'm using IBM hardware. For this mission, I'm using operating system is HP Unix. Okay, operating system HP Unix. Hardware is HP hardware. For this mission, I'm using operating system is Red Hat, and hardware I'm using Intel hardware. Let's understand the heterogeneous cluster means you can take any hardware and any operating system, any operating system, any operating system, any operating system for missions in cluster, missions in cluster. It is not required to, it is not required to take same operating system and same hardware for all systems, all machines. You can take any hardware, you can take any operating system team. Hadoop supports all operating systems. Hadoop supports all hardwares. You can take any hardware, you can take any operating system. So this process we are calling heterogeneous cluster. Heterogeneous cluster means you can take any operating system, any hardware for any mission in cluster. Okay. Next, very important feature is scalability. Scalability. Every feature is very important. What is scalability? Let's say team, let's say our client is small client. So initially we created a cluster, one master, 3 slave missions. One master and 3 slave missions. Initially we created one master and 3 slave missions. So initially we created this cluster for client XYZ. For client XYZ, we created master with 3 slave missions, 4 node cluster, 4 node cluster team. Workers are slaves. Okay, we created one master and 3 slaves. One master and 3 slaves team. So later business is grown and we want to add. You can add any number of missions. You can add any number of missions to existed cluster without stopping, without putting in maintenance mode. You can add, remove any number of missions. You can add or remove any number of missions to existed cluster. Okay, so you can add or remove any number of missions. You can add or remove any number of missions. Any number of missions. Number of missions to cluster without putting in maintenance mode, without putting cluster in maintenance mode. Maintenance mode or without stopping cluster, without stopping cluster team. You can add any number of missions. You can increase your cluster size. There is no limit in Hadoop cluster. There is no limit in Hadoop cluster. There is no limit in Hadoop cluster team. That's why we are saying Hadoop supports what? Hadoop supports unlimited storage. Hadoop supports unlimited storage. Okay. We can easily remove, we can easily add missions to cluster. Like third-party vendors like Cloudera. Cloudera gives admin interface. Through the admin interface, we can add, we can remove. We have Apache provided, Apache also provided admin interface, Ambari, Apache Ambari. You can use Apache Ambari to add, remove missions from cluster into cluster. Okay. So these are 8 important features too. These are 8 important features. Cost effective, large cluster of nodes, data, distributed data, parallel processing, automatic failover management, data locality optimization, heterogeneous cluster, scalability. These features makes Hadoop is more powerful. Because of these 8 features, most of the people using Hadoop as their storage. Hadoop as their storage team. Okay. Understand, right? 8 important features. Let's start. In this session, we are going to discuss Hadoop architecture. Hadoop architecture. Hadoop follows master-slave architecture. Hadoop follows master-slave architecture. Hadoop follows master-slave architecture. In Hadoop architecture, there are 5 demands involved. In Hadoop architecture, there are 5 demands involved. They are: 1, NameNode. Second one, secondary NameNode. And third one, DataNode. Fourth one, until Hadoop 1.x, job tracker. Okay. From Hadoop 2.x, ResourceManager. So they replaced, Apache people replaced job tracker role with ResourceManager. Fifth one, until Hadoop 1.x, let's say take same thing. Fifth one, until Hadoop 1.x, task tracker. So task tracker role replaced with NodeManager. team. So until Hadoop 1.x, task tracker is implemented. From Hadoop 2.x, NodeManager is replaced task tracker role. So these are 5 important demands team. First one, what is daemon? A daemon is a process. A daemon is a process. It always runs in the background. Runs in the background. A daemon is a process. A daemon is a process, it always runs in the background. In Hadoop, daemon means it's a Java program. Daemon means it is a Java program. It is a Java program. Okay. So in these 5 daemons, we have master daemons team. Master daemons. NameNode, secondary NameNode, and third one, ResourceManager. These are master daemons. Slave daemons are one, DataNode, and second one, NodeManager. These are slave daemons. Let's see master slave architecture. Hadoop master slave architecture team. Hadoop master slave architecture. So we take master missions to separate mission team. We take master missions to separate mission. So resource manager, next one, NameNode, and next one, secondary NameNode. These are masters. Next one, slave missions. DataNode and NodeManager. DataNode and NodeManager. Okay. So we take multiple slave missions team. Okay. So one important point here, it is highly recommended. To take master daemons and separate missions. Next one, it is highly recommended. It is highly recommended. Highly recommended to take both slave demands on same mission. Slave demands on same missions. Same missions. We will take multiple slaves. We will take multiple slaves. Understand, right? Hadoop architecture, master slave architecture. This is Hadoop master slave architecture. Hadoop follows master slave architecture. Now let's understand HDFS architecture. HDFS architecture. In HDFS architecture, we have three demands still. HDFS architecture is responsible for HDFS architecture is responsible for storage. HDFS architecture is responsible for storage. So we have demands, HDFS demands. One NameNode, second one secondary NameNode, and third one DataNode. Third one DataNode. So these are HDFS demands. In this master demands, NameNode, secondary NameNode. Slave demands are DataNode. Slave demands are DataNode. In HDFS architecture, slave demands are DataNode. Let's see. We'll take NameNode and secondary NameNode as a master, and we take multiple data nodes. We will take multiple data nodes. So here we take NameNode and secondary NameNode. Okay, so these are masters and these are workers. So data node. HDFS architecture. Okay. So in HDFS architecture is responsible for taking storage request, receives storage request. So DataNode is responsible for storing the data. Coming sessions, I will explain each daemon purpose thing. Okay. So HDFS architecture is for responsible for storage. Here we have three daemons: NameNode, SecondaryNameNode, DataNode. Master daemons NameNode, SecondaryNameNode, and slave daemons DataNode. We take multiple slave nodes. We will take 1 or 2 or 3 missions for master missions. For high availability, we take multiple master missions. Okay. Let's understand MapReduce architecture. MapReduce architecture team. MapReduce architecture. MapReduce is responsible for processing. MapReduce is responsible for processing. Okay. So here in Hadoop, we have two MapReduce architectures. Two MapReduce architectures. They are until Hadoop 1.x. Until Hadoop 1.x. Until Hadoop 1.x, we have job tracker, and second one task tracker. This architecture we call MR1 architecture. And other architecture introduced in Hadoop 2.2. From Hadoop 2.x, MapReduce 2 architecture is introduced. MapReduce 2 architecture is introduced, MR2. So this architecture we call it as yarn architecture. Okay. So in this architecture, in place of job tracker, they replaced with resource manager. In place of task tracker, they replaced with NodeManager team. In place of job tracker, they replaced with resource manager. In place of task tracker, they replaced with NodeManager. So in this master daemons are resource manager. Slave daemons are NodeManager. Okay, let's see architecture diagrammatically. So we take one or more master daemons, that is resource manager, and we will take multiple node managers. So we'll take multiple node managers team. So this is MapReduce architecture. MapReduce architecture. So this architecture is responsible for processing request. So it may be MapReduce, it may be MapReduce, it may be Pig, it may be Hive, it may be Flume, it may be Scoop, it may be Spark, etc. So any processing request, it receives any processing request team. So resource manager can take any processing request assigns to node manager. So this is a master, and these are workers. Okay. Understand, right? MapReduce architecture team. In MapReduce architecture, we have two daemons, resource manager and node manager. Resource manager is a master daemon. It will take any processing request, assigns that processing request to node manager. Node manager is responsible to process. In HDFS architecture, NameNode is responsible to take storage request and prepares metadata, returns that metadata back to client. Client is responsible to write data into DataNode. And here secondary name node purpose is different. I will explain each concept, each daemon independently so that you will understand clearly. Okay. Did you understand him? MapReduce architecture? In MapReduce architecture, we have these daemons. Okay. Let's start. So in this session, we are going to discuss Hadoop components. Hadoop components. So there are 5 important components. There are 5 important components. They are 1 NameNode, second one secondary NameNode, and third one DataNode, and fourth one until Hadoop 1.x, job tracker, from Hadoop 2.x, job tracker is replaced with resource manager. Okay. Next, fifth one until Hadoop 1.x, task tracker team. And from Hadoop 2.x, task tracker is replaced with node manager. Okay, we are going to discuss each demand in depth. So these are 5 important demands, 5 important components, or 5 important demands which plays very important role in Hadoop. These 5 demands plays very important role in Hadoop team. Yep. So first let's start with demand. First demand. Before going to start this demand, so these are these 5 demands plays very important role. Very important role. Important role in Hadoop. So first one, daemon means it's a background process string. Daemon means it's a background process. It is a background process. One. Yep. Daemon means background process. Background process. Whenever we start Hadoop, these 5 demands runs in the background tape. These 5 demands runs in the background. Each demand has its own roles and responsibilities. Every demand has its own roles and responsibilities. Okay. So let's discuss each demand one by one. Let's discuss first NameNode. First one, NameNode. What is NameNode? What is NameNode? So first one, NameNode is a HDFS daemon. HDFS daemon. It is a master daemon in HDFS. It is a master daemon in HDFS. HDFS. Let's first diagrammatically discuss about NameNode team. First one, NameNode. NameNode. So NameNode is a master daemon. NameNode is a master daemon team. NameNode is a master daemon. So it receives a client request. It always receives storage request. From client, it will receive always storage request. Let's say we have a client. So client want to place a data. So client want to place a data, file one, and file one size is 300 MB. 300 MB. Okay. Let's say 300 MB file you want to store into Hadoop cluster. So this is my client mission. Client mission. Okay. So client mission first communicate with NameNode. First client communicates with NameNode. Sends request for storing the data. So first client sends request to NameNode team. So client communicates client communicates with NameNode. Client communicates with NameNode to store the data. To store the data. To store the data. When NameNode receives storage request, when NameNode receives storage request, it will read some configuration files. It will read some configuration files. First one, it will read HDFS-site.xml file. From this, it will understand block size. Block size. It will understand block size. Next, it will understand replication factor. Replication factor. So default block size is 128 MB. 128 MB is a default block size. Default block size. Replication factor is 3. This is default. Default. If there is no configuration for block size, replication factor, then NameNode understands default block size is 128 MB. Replication factor is 3. Okay. Next one, it will read slaves file. Slaves file. Here we provide complete information of slaves files, slave missions. How many slaves are presented in our mission? We will provide complete information of slaves in this file team. Next one, it will read proximity algorithm. Proximity algorithm. In this proximity algorithm, it contains racks information. Okay, and bandwidth of each mission. Bandwidth of each mission. We call this is a we call this one rack awareness algorithm. Rack awareness algorithm. This algorithm presented in Python script. This algorithm presented in Python script file. So NameNode reads a proximity algorithm or rack awareness algorithm, understands in which rack data nodes are presented. What is bandwidth of each mission? Okay, so it will read all these. Mainly, these are 3 important files team, and additionally it will read some other files. Okay, then it will prepare metadata. So first one, when NameNode gets storage request, when NameNode gets storage request, when NameNode gets a storage request, it will read HDFS-site.xml file, HDFS-site.xml for block size, comma, replication factor. So default block size is default block size is 128 MB. Default replication factor is 3, and it will read it will read slaves file for understanding where is data nodes, where is data nodes, where is data nodes. Next one, it will read proximity algorithm or rack awareness algorithm. Rack awareness algorithm to understand racks, okay, bandwidth of each mission, bandwidth of each mission. Rack is a collection of missions. Rack is a collection of missions. Okay, so by reading proximity algorithm, it will understand how many racks are presented. In each rack, how many missions are presented, how many data nodes are presented. So based on this, it will allocate rack 1, block 1. Same block 1 duplicate copy may be presented in rack 2. Same block replicated block is presented in another rack. It will not place same blocks in same rack. Let's say block 1 contain 3 duplicate copies. One block it place in rack 1, one block it place in rack 2, one block it place in rack 3. In that way, it will prepare metadata thing, because there may be a chance of down of rack, right? Yes or no? That's why it always reads rack awareness algorithm to understand rack's information. Let's say rack 1 is a high bandwidth. So first 2 blocks it will place in rack 1, because rack 1 is very faster and rack 2 is nearest to client. So it will check nearest location as well as bandwidth. Okay, lot of factor it will consider thing. NameNode, before placing file into Hadoop cluster, it will read all this information. Okay, then it will prepare metadata. It will prepare metadata. Okay, so let's say it is prepared metadata. Metadata about file 1. So file 1, block 1, first mission, third mission, fifth mission. File 1, block 2, second mission, fourth mission, sixth mission. File 1, block 3. So it prepared third mission, fourth mission, fifth mission. Assume it is prepared in this way. Okay, then it will prepare metadata. What is metadata? What is metadata? Metadata means data about data team. Data about data. Definition is data about data. It has file to block to data nodes mapping, block to data nodes mapping thing. File to block to data nodes mapping information. So it has a information of block to data node, file to block to data node mapping thing. Okay, So it will prepare metadata, then it will return metadata to client, Once a client receives metadata, see, once it prepares metadata, right? This metadata information, it will return back to client team. Hey client, this is the metadata. So you can copy this metadata. Okay, it will prepare this metadata information back to client. Okay, so next important to note. So before going to start DataNode, let's understand the secondary name node. Let's start. We understand what is NameNode. Then now let's understand secondary name node. What is secondary name node? Say team, generally most of the people, by seeing secondary name node, they think that it is a backup node. First important point, it is not a backup node. It is not a backup node for name node. It is not a backup node for name node. It is a HDFS daemon. It is a HDFS daemon. It is a master daemon. It is a master daemon in HDFS architecture. Okay, so it is a master daemon in HDFS architecture. Then what is the purpose of this secondary name node? What is the purpose of this secondary name node? Let's diagrammatically discuss, team. Let's diagrammatically discuss. So first one, let's copy this part. Now let's understand purpose of this secondary name node. Purpose of secondary name node. Secondary name node. What is the purpose of secondary name node? Secondary name node is a check pointing node. It is also called check pointing node. It is also called check pointing node. Check pointing node. It is also called check pointing node. It will perform check pointing operation. It will perform check pointing operation. What is check pointing operation? So here, let's understand diagram, team. So client, whenever client want to place data, client approaches what? Name node mission. Yes or no? Client approaches name node mission. Name node prepares metadata. After preparing data, okay. So it prepared metadata and it stores metadata into metadata file, or this file also called FS image team. Let me copy this one. here. This file also called FS image. FS image. FS image means file system image. File system image. So this file also called FS image. Metadata presented in RAM. FS image presented in hard disk thing. So for this FS image, it will create memory in a RAM. We call that memory is a metadata. So for every client request, it will not directly write into metadata. NameNode not writes into metadata. There is one more file. Edit log file. There is one more file, edit log file team. Edit log file. Edit log file. In this edit log file, there are multiple segments. Multiple segments team. Let's say client is writing a file. Let's see. Write file 1. Write file 1 or file 2. Write file 2. Next one. Append to file 1. Append to file 1. Next one. Remove file 2, etc. So it contains some other information too. So for any client request, NameNode will not update directly into metadata. It will first write into edit log file. Every entry in a edit log file, we call it as a segment. So this is called segmenting. Each entry in a edit log file, we call it as segment. So edit log file contain multiple segments. So initially NameNode writes into edit log file. Now let's understand secondary NameNode purpose. Secondary NameNode performs merging metadata or FS image and edit log files. Merging FS image. Okay. Merging this edit log files. And creates a new FS image. Merging edit log files, merging metadata, and creates a new FS image. And it will merge all entries. Team. FS image entries and edit log entries, and creates a new file. Then finally, this process is called checkpointing. This merging edit log file metadata, we call it as a checkpointing. First one, it will perform checkpointing operation. Merging FS image, and edit logs. Is called checkpointing. Merging edit logs and FS image is called checkpointing. Yep. So once it merges edit logs and metadata, then it will overwrite this new FS image with old FS image thing. it will overwrite. So old FS image data overwrite with the new FS image. Then it will remove all entries from edit log file. Then edit log is now empty. Once a new FS image is written into FS image file, then this edit log file become empty. So merging FS image and edit log is called checkpointing. Once checkpoint is completed, it will erase edit log file. Then new entries are going to enter into edit log file. Okay. When checkpointing operation happens, that is very important. When checkpointing is happen, there are two scenarios. They are one, edit log file size, and the second one, time, threshold time. So what is the size of edit log file? What is threshold time? What is the edit log file size, or what is threshold time? Threshold time or number of entries. Okay, let's see secondary name node configuration in Apache documentation. Checkpointing in Hadoop Apache documentation. So let's see HDFS user guide. Let's first go. So DFS dot NameNode dot checkpointing period is 1 hour default. Understand, right? 1 hour is a default. And next one, 1 million transactions. So this is the property thing. This is property. And checkpointing transactions, 1 million transactions. Default is 1 million transactions. 1 million transactions. Number of entries or transactions are 1 million transactions. So whichever reaches first, maybe 1 million transactions reached before 1 hour, or 1 hour reached first. Maybe any one property. It may be 1 million reached, or edit log time is reached with 1 hour. Then it secondary name node performs checkpointing. Secondary name node performs checkpointing. Without secondary name node, NameNode can perform checkpointing, but it is overhead on NameNode. So to avoid this overhead, Apache people or Hadoop people introduced secondary name node team. Understand, right? Secondary name node is not a backup of name node. It is a checkpointing node. Okay. Now let's understand DataNode. DataNode is a DataNode is a HDFS daemon. HDFS daemon. It is a slave. It is a slave daemon. It is a slave daemon. Slave or worker daemon. Worker daemon. Worker daemon thing. It is a slave daemon or worker daemon. Let's diagrammatically understand. Let's understand it. So first one, data node is a slave daemon. We can take n number of data nodes. We can take n number of data nodes. So there is no limit. You can take n number of data nodes. We can take n number of data nodes. We can take n number of data nodes. We can take n number of data nodes. The main purpose of data node is to store the data. The main purpose of data node is to store the data. First important point, to store the data team or to hold the data. To store the data or hold the data. Team. So who will write data into data node? Client will write data into data node team. So once client got metadata information from NameNode, once client got metadata information from NameNode, then client will perform HDFS write flow. We will discuss what is HDFS write flow in HDFS concept team. So once client got metadata information, client will write data into HDFS, data nodes. So this process we call it as HDFS write flow. So client will write data according to metadata. Let's say block 1 is presented in 1, 3, 5th mission. Yes or no? So this is block 1. Block 1. Next one, client will write block 2, 4, and 6. let's say client is written block 2 here, block 2, block 2, and client is written block 3 in third mission, fourth mission, and fifth mission. So block 3, block 3, and block 3. So client will write data into data node stream. These are different data nodes. Data node 1, data node 2, data node 3, data node 4. You can take n number of data nodes. Data node 5, data node 6. So you can take n number of data nodes. Data node purpose is to store the data. Who will write the data into this mission? Client will write the data into data nodes. First, client communicates with the NameNode. Before writing, client will communicate with the NameNode to write the data. NameNode prepares metadata, then returns that metadata information back to client. Then based on that metadata information, client will write the data into data node stream. So main purpose of data node is to store the data, and it updates its master node. It updates its master node saying number of blocks, saying I have so and so blocks. First one, I will say I am active, and I have so and so blocks. So it will update NameNode, a NameNode first. These data nodes, data node 1, data node 2, data node 3, data node 6 will communicate with the NameNode. A NameNode, I am active, I have so and so blocks. Then NameNode verifies metadata. Is data node 1 contain only block 1? Yes, correct. Then data node 2 sends signal saying I am active, I have so and so blocks. Then NameNode verifies metadata. Then finally it will confirm blocks are properly presented in data node missions. If any mission is not working, then it will do some other operation. We will discuss in HDFS file system. Okay. Understand, right, team? So data node purpose is storing the data and communicating with its master node, and updates information I am active and I have so and so blocks. This process, this concept is called heartbeat signal. Heartbeat signal thing. So updating information to its master node is called heartbeat signal. When data node sends a heartbeat signal, that is presented in HDFS file system, HDFS-site.xml file. In that file, we will configure time, heartbeat signal time. Okay. So based on that heartbeat signal time, data node will communicate with NameNode and updates this information. Okay. Understand, right? What is data node? Now let's understand resource manager. Resource manager is a MapReduce daemon. it is a it is a it is a yarn daemon. Yarn means yet another resource negotiator. It is MR2 architecture. MR2 architecture. It was introduced in Hadoop 2.x. It is introduced in Hadoop 2.x. It is a MapReduce daemon or yarn daemon type. Let's diagrammatically discuss. Team. Let's diagrammatically discuss. Okay, we have a resource manager. And resource manager receives client request. Resource manager receives client request. Resource manager receives client request. Resource manager receives processing request. So this is client mission. So first one, resource manager receives processing request. This processing request may be MapReduce request. Processing request may be pig request. Processing request may be Hive request, Scoop request. Okay, it may be Spark request, etc. It may be any of these team. It may be MapReduce, it may be Scoop, it may be Hive, it may be Spark, it may be any processing request. Any processing request team. It will take any processing request. So any big data request, any big data processing request, any big data processing request. So once a client, once a resource manager receives this request, okay, once resource manager receives processing request, once resource manager receives a processing request, it will communicate with NameNode. It will communicate with NameNode. First, it will communicate with NameNode team. It will communicate with NameNode. NameNode, I want to file 1 or file 2. Let's say in this MapReduce application or Spark application, we want to read file 1. So this resource manager communicate with NameNode. NameNode, I want to file 1 information. Then NameNode reads metadata. NameNode reads metadata team. NameNode reads metadata of that file 1 and sends that information back to client. A client, this is file 1 information. File 1 information. So it gives complete information of file 1. So it contains complete information of different files, right? Metadata has information of different files. File mappings, yes or no? So NameNode reads metadata and returns that metadata information back to ResourceManager. ResourceManager, these are different blocks for file 1. It present in different missions. Complete information it returns back to ResourceManager. Okay. So once ResourceManager receives a processing request, it will communicate with the NameNode. It will communicate with the NameNode for details of client requested file, client application required file. Once ResourceManager receives response from once ResourceManager receives response from NameNode, then based on the data and locations, it will assign tasks to its slave missions. Its slaves or workers team. Its slaves or worker missions. After identify blocks information, let's say block 1 is presented in mission 1, block 2 presented in mission 3, block 3 presented in mission 5. Then based on this information, it will assign task to mission 1, mission 3, mission 5. Okay. So ResourceManager first receives a processing request and gets the information from NameNode, requested file information, then assigns a task to corresponding missions team. Its slave missions. Its slave mission is NodeManager. So ResourceManager slave mission is NodeManager team. Okay. Now let's understand NodeManager. NodeManager is a slave or worker daemon in MapReduce architecture. In MapReduce architecture team. Slave daemon or worker daemon in MapReduce architecture. The responsibility of NodeManager is to process client request. To process client request. Client request may be any of this request. Team. So client request may be any of this request. Client request may be MapReduce, Pig, Hive, or Scoop, or Spark, any of this big data processing request. Let's diagrammatically discuss it. Okay, so once it receives a client request, resource manager communicate with the NameNode, get the metadata, and identifies missions. Then it will assign task to corresponding missions team. Let's say we have 6 missions. So these are different node manager missions. So these are different node manager missions. Let's say block is presented here. Firewall block is presented here. Block is presented here. Let's say block is presented here. Assume this is block 1, block 1, block 2, block 2, block 3. Let's say 3 blocks for file 1. Then it will start this big data processing request here, here, and here. Then this node manager is responsible to process this block through this request. It may be MapReduce request, it may be pig request, it may be hive request, it may be scope request, it may be Spark request, any big data processing request. Your processing request is created in all the data locations team, all the data locations, wherever data presented for that file, it will create a parallel process. So node manager is responsible to process that data. So whatever the statements we write in MapReduce, pig, hive, scoop, Spark, right? Those instructions execute parallelly in node manager missions. Node manager missions. Node manager is responsible to process your data team. Understand, right? So this is node manager architecture. So once node manager receives processing request assigned by its master, then it will create, then it will start processing. Okay. After that, next important responsibility of node manager is node manager updates status to its master saying I am active, I am executing so and so request. I am executing so and so request or task, request or task, so and so request or task, and 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 percentage of completion, percentage of completion. Let's say 10% completed or 20% completed. So it updates this information. So this process is called heartbeating. This process is called heartbeat. Heartbeat. Heartbeat signal. Heartbeat signal in MapReduce. MapReduce architecture team. In MapReduce. Understand, right? That's it for NodeManager team. Okay. So understand, right? What is NameNode? What is SecondaryNameNode? What is DataNode? What is ResourceManager? And what is NodeManager? And I'm going to add one more important component is client. Client. Hadoop important component is client. Okay. Let's discuss about client. Let's discuss important one. Sixth component is client. What is client? Let's discuss diagrammaticality. So first one, we have a Hadoop cluster, master machines, and we have multiple worker machines. Multiple worker machines. Let's say this is our Hadoop cluster. This is our Hadoop cluster. Okay. Clients, we have clients. We have two types of client setting. Clients, we have two types of clients. There are two types of clients. Two types of clients. Here, HDFS clients, HDFS clients. Okay. Second one, processing clients. Processing clients are applications. Okay. So here, let's say clients. So first one, first two clients. Let's understand first client. First important client team, HDFS CLI. So first one we have HDFS CLI or B-line tool. We use HDFS CLI or B-line tool. So HDFS CLI, B-line tool, GUI user interface or application clients. Application clients like application clients. Application clients. So you can write either Java program, we can write either Java program, we can write either Python program, Scala program, or we can write a Python program, etc. Hadoop supports plenty of languages too. Plenty of languages. So by using these clients, we can read or write data into write data into the system setting. Okay. So by using this clients, we will read or write data into Hadoop cluster. So client may be HDFS CLI, client may be beeline tool, client may be GUI user interface, client may be Java program, client may be Scala program, client may be Python program. Okay. Let's say to write data, to write data, to write data, data. Let's say Python, example I am taking, Python plus HDFS API, HDFS API. Then we will write into HDFS file system team, HDFS file system, HDFS file system. By using HDFS API, we can connect Hadoop cluster. Then we can write the data into Hadoop cluster. So you can directly using this Hive CLI, we can execute commands team, HDFS commands. We can execute HDFS commands. By using Hive CLI, we can execute HDFS commands. This one is a graphical user interface. GUI is a GUI interface. Graphical user interface. GUI interface. We can upload files. Upload files. This is simple. But if you want to give a front-end user interface, or you want to write one nice user interface, there we want to give a access to the client to upload a file. That application may be developed in Angular, maybe React.js, maybe HTML5, etc. In front end, we want to give a nice user interface. Client selected a file, then client want to load through that screen. Client want to load data into Hadoop cluster. Back end, we write either Java program or Python program or Scala program. It internally uses HDFS API. So front end application communicates with middleware application like Java, Scala or Python and gives file path. Then Java application reads that file and uploads that file into Hadoop cluster. Understand, right? You can directly write HDFS commands, or you can write a nice user interface. That user interface can be accessible throughout the world. HDFS CLI only available for the developers, testers, and administrators, not for clients. Yes or no? So if you want to give a access to client to upload their files into Hadoop cluster, we can create a nice user interface with UI technologies. Then user can upload their application using this application clients team. Okay, so we have command line clients, we have graphical user interface clients, we have application clients. Application client you can develop by using any programming language. Okay. So here internally these application clients uses HDFS API. API nothing but application programming interface, set of predefined classes, functions. By using that predefined classes and functions, we can communicate with the Hadoop cluster. We can write the data into Hadoop cluster. So here master may be masters are resource manager, name node, secondary name node. Here clients are DataNode and NodeManager. Okay. Understand, right, clients? Team, did you understand what is the role of clients? So these are 6 important components of Hadoop team. 6 important components of Hadoop. Yeah, first let's understand what is HDFS file system. HDFS file system is a Hadoop distributed file system team. HDFS file system stands for Hadoop distributed file system team. Hadoop distributed file system. Whenever we store data into HDFS file system, data divides into multiple blocks. Data divides into multiple blocks and stores across the cluster. Let's diagrammatically understand it. Let's diagrammatically understand. We have Hadoop cluster. We have a master. We have master. Let's say this is master. And master demands, we have 3 demands. Means demand means background process, resource manager, NameNode, and resource manager, NameNode, and secondary NameNode team. NameNode and secondary NameNode. So we have different demands team, master demands. We have worker demands team. Let me take. We have different worker demands. We have different worker demands team. So worker demands, always we use DataNode and NodeManager team. DataNode and NodeManager. DataNode plus NodeManager. Okay. So RM means resource manager team. Resource manager. NN means NameNode. And SNN means secondary NameNode. And DN means DataNode team. NM means NodeManager. So whenever client mission, client want to store data. So this is client mission team. Client. We have file. Let's say this is a file. So file name is file1. And client want to store this file, 300 MB data file. So 300 MB data file. So client first send a request to master mission team. Hey master, I want to store 300 MB file data. 300 MB file data. So this request reach to NameNode team. So NameNode is responsible for storage request team. NameNode is responsible for storage request. Then NameNode prepares metadata. NameNode prepares metadata team. NameNode prepares metadata. NameNode prepares metadata. So let's say it says file one. Yeah, first important point to team. File divided into multiple blocks. In HDFS file system, file divided into multiple blocks. In HDFS file system, file divided into multiple blocks. Multiple blocks. Each block size until Hadoop 1.x, until Hadoop 1.x 64 MB, 64 MB. From Hadoop 2.x, it is 128 MB, 128 MB. So 300 MB data by 128 MB. So we will get three blocks. Block 1 with 128 MB, block 2 with 128 MB, 128 MB, block 3 with 128 MB. So we get three blocks. Block 3 contain 44 MB because remaining 128 plus 128 remaining is 4 MB. So we get three blocks. And one more important point to team. Hadoop supports normal hardware. Normal hardware failure chances are high. So to resolve failure fault tolerance, Hadoop replicates each block 3 times. Each block 3 times. So based on this, it will prepare metadata time. So here it will prepare metadata. File 1, block 1. Place this block 1 into first mission, third mission, fifth mission. First mission, third mission, fifth mission team. Next one, place file 1, block 2 into first mission, second mission, fourth mission, sixth mission. Next, place block 3 of file 1 into, let's say 3, 4, 5. One important doubt here, team. How it will decide DataNode missions. DataNode is responsible to store the data, team. DataNode is responsible to store the data. One more important point. DataNode is responsible for storing the data. How? NameNode decides where to store blocks. Where to store block. Where to store means in which data node to store. In Hadoop, there is one important algorithm, team. In Hadoop, there is one important algorithm. There is one important algorithm called proximity algorithm, team. Proximity algorithm. Team. There is one important algorithm called proximity algorithm. What is this proximity algorithm? Proximity algorithm has data center details, rack details, rack details, data center details, rack details, node details, node details, node details, bandwidth, Ethernet, Ethernet details, Ethernet bandwidth. So it contain all these details team, proximity algorithm. So NameNode uses proximity algorithm and identify distance of each mission and identify bandwidth of each mission, okay, identifies bandwidth of each mission and distance of each mission to client and data center details, rack details, mission details, etc. After identifying, then NameNode prepares metadata type. NameNode prepares metadata. NameNode prepares this metadata type. It is decided this information. Then after preparing this metadata team, NameNode returns this metadata to client mission. Hey client, this is the metadata to place your file. Then client is responsible to perform write floating. First client request NameNode to place file. Then NameNode prepares metadata, returns metadata back to client. Once metadata it receives, client is responsible to write the data into HDFS file system. Client is responsible to place the data into HDFS file system team. So master prepares this metadata. NameNode prepares this metadata by following these steps. First, block size. Next, replication factor. Next, proximity algorithm. Based on all these parameters, it will prepare metadata. Then client writes data into HDFS file system team. So block 1, it is writing into DataNode 1, DataNode 3, and DataNode 5. So this is block 1. And block 1. And next one, block 2 stores in DataNode 2, DataNode 4, and DataNode 6. So block 2, and block 2. So next one, block 3 team. Block 3 it places in 3 according to metadata. Client places in 3rd mission, 4th mission, and 5th mission team. 5th mission. So it will places block into 4th mission, block 3, 3rd mission, 4th mission, and 5th mission team. So in this way, HDFS file system distributes across the cluster. In this, we have 6 worker missions team. In production, in live systems, we may have multiple missions. Team. Understand right team? HDFS file system is a distributed file system. Whenever client want to place data, file divided into multiple blocks. How block size is decided? Until Hadoop 1.x, it is 64 MB. From Hadoop 2.x, it is 128 MB. Then how it will decide, how it will prepare metadata based on these parameters team. So first parameter is block size. Second parameter is replication factor. Third parameter is it identifies data node missions based on the proximity algorithm. Most of the time, most of the time, administrators writes proximity algorithm in Python language, Python scripting. So proximity algorithm they define in Python language, team. So NameNode reads the proximity algorithm, defines data node missions. Clear writing? HDFS file system. What is HDFS file system? Clear, right? HDFS file system is a distributed file system. If anyone wants to store data into HDFS file system, your data divided into multiple blocks. Each block size is minimum 128 MB from Hadoop 2.x. Block size is 128 MB. Okay. One important point to think. As part of this course, we are going to use data sets. Team. So data sets you can download from this location, team. This is my Git repository. Open browser and download data from this repository. I'm going to upload many files in this repository, team. Under C family in, you can see data directory. You can use download zip file. You can download this entire data set, team. So practice purpose, I am going to use these data sets. And one more important one is, we have one video for virtual machine setup. So youtube.com/cfamilycomputers. Here we have one video, team, videos. So this is the video, team. I recommend this video, team. I'm putting in, keep sending in chat box. So go to this video, set up Hadoop virtual machine, team. Set up a Hadoop virtual machine. There I have explained clearly how to set up a virtual machine, what are the softwares are required, and what are the softwares I have installed. So go to that video and set up a Hadoop virtual machine, team. So there is one more course here under cfamily.com. Here you see big data section. Under big data section, you can see Hadoop virtual machine setup. So I recommend this one, team. This is the link. Link to set up Hadoop virtual machine, big data virtual machine, team. I have installed many softwares. You can follow this link. This is the course, free course, team. You can register this free course and complete this one, team. So here I have explained how to install and configure. If you get any issues, how to troubleshoot. I have explained all the videos, all the concepts. Try to set up whatever the practical part we are going to discuss HDFS. So HDFS we are going to see, team. First we start with we start with HDFS introduction team. What is HDFS? After that, we are going to see what is block. Okay. Next, we are going to see replication and replication factor. And next, we are going to see over replication. Yeah, over replication and under replication, over replication and under replication. Okay. Next, HDFS write flow. I said when user want to write data, he will perform write flow. When user want to read data, he will perform read flow. HDFS write flow, HDFS read flow. Then we are going to discuss HDFS commands team. Here we are going to discuss HDFS commands, in-depth HDFS commands team. Whatever the commands we are going to practice, right? Whatever the commands we are going to practice, for all the commands, I am going to use this data team. This is the data. So data sets are presented in GitHub team. So I recommend all of you to download data from this location. So data sets you can download from this location. Datasets you can download from this location too. So as part of HDFS file system, we are going to discuss in-depth HDFS file system, including practical part and virtual machine, big data virtual machine you can download from this one too. This is the link. So this is the link team. This is the link to set up big data virtual machine team. So this is the link. This is completely free course team. This Spark and Hadoop virtual machine. This course is completely free. So you can go to cfamily.com under big data section. You can click on development. Here you can see Apache, Hadoop and Spark virtual machine. Here I have explained what is Hadoop virtual machine and how to install Oracle VirtualBox, how to download start big data virtual machine, and how to start Hadoop daemons, how to access NameNode, how to start a pig, etc. All these options I have explained. Okay, if there is any issue, you can see here. Then you can download this resources file. You will get a Google Drive link. From there, you can download virtual machine for our practice purpose team. So this is end-to-end HDFS workshop team. Complete HDFS related classes we are going to discuss in this session team. Later I am going to add some more concepts. Okay, later I may going to add some more other concepts. These are the main important concepts we are going to discuss as part of HDFS file system. Yeah, now let's understand what is HDFS block. What is HDFS block? HDFS block means it's a chunk of data or piece of data team. Block means block is a chunk of data or piece of data chunk of data or piece of data type. Chunk of data or piece of data. Let's first understand normal file system. Means in any operating system we have a file system concept, right? Let's understand normal file system concept. We have already here, right? So let me take a normal file system thing. Normal file system. Let's understand normal file system. Normal file system team. So whenever user places data into system, let's say this is my system. So whenever user want to place 300 MB file, 300 MB file. User want to store 300 MB file. File name is F1. Okay. File name is F1. So first point thing, normal file system is not distributed. Normal file system is not distributed. Okay, not distributed. So it will not store in multiple machines. It will store in a single machine. First important point to take. Normal file system block size. Normal file system block size is 4 KB in old operating systems and 8 KB in new operating systems. 4 KB in old operating systems, 8 KB in new operating systems. So this is normal file system. So normal file system also divides into multiple blocks. Normal file system also divided into multiple blocks. It will store in a single machine. Okay, so it is not distributed. It will store in a single machine, and here it divides into multiple blocks. It divides into multiple blocks. But what is the block size? 4 KB. In latest operating systems, it is 8 KB. So seeking time means reading time. Reading time is slow in normal file system. Coming to HDFS. HDFS block size is until Hadoop 1.x, it is 64 MB. From Hadoop 2.x, from Hadoop 2.x, it is 128 MB. 128 MB. From Hadoop 2.x, it is 128 MB. And HDFS block is distributed across multiple nodes. HDFS blocks are distributed across the cluster, across the cluster team. HDFS blocks are distributed across the cluster team. Okay, across the cluster team. And block size is 64 MB until 1.x. From 2.x, it is changed. And one more important point, team. One more important point I forgot to cover in HDFS. HDFS file system is user space file system team. HDFS file system is a user space file system. HDFS file system is a user space file system. Normal file system loads as part of operating system process. But HDFS file system loads as part of user process. Whenever we start Hadoop server, then only HDFS file system starts. When HDFS server starts, whenever user executes start commands. Yes or no? That's why we are saying HDFS file system is a user space file system. It starts as part of user process, but normal file system starts as part of operating system team. So next important point, team, coming to blocks, coming to HDFS blocks, team. Sorry, let me copy this one. So normal file system loads as part of operating system, but HDFS file system loads as part of user process. So we can customize HDFS block team. HDFS block. We can customize HDFS block. We can increase or decrease HDFS file system size. HDFS file system size. So to increase HDFS file system size, decrease HDFS file system size, we use one configuration file called HDFS-site.xml file team. HDFS file system, HDFS-site.xml file. Default is 128 MB. If you not configure, default is 128 MB. So let me go and check HDFS-site.xml. HDFS-site.xml. Here, this is the first link. Go to this one. Check block size. HDFS block size team. This is HDFS block size. sorry. Yeah, this one, DFS dot block dot size. So this is the parameter term. So in HDFS hyphen site.xml file, HDFS hyphen site.xml, site.xml, there is one configuration root tag and configuration end tag. In between this, we write one property tag team. In between this, we write one property tag, property tag, property tag. In this, we use name equal to, there is one more sub element called name, sorry, name. And in this, we use DFS dot block size, name, and value. Here we can specify custom size. Here we can specify custom size routine. Once you install Hadoop, right, there is one XML file in Hadoop configuration location. In that, we can customize our block size. Default block size is 128 MB. Default block size is 128 MB from Hadoop 2.x. Before Hadoop 2.x, it is 64 MB. Clear, right, team? Before Hadoop 2.x, it is 64 MB. From Hadoop 2.x, they changed 128 MB. What is the advantage of bigger size? Reading time is very faster. Reading time is very faster. The main advantage of bigger sizes, the main advantage of bigger block size is seeking time, means read time is very faster. Let's say team, coming to here, 4 bytes, latest version 8 bytes, 8 KB at a time. Here 128 block at a time. Which is faster? 128 block is faster. Reading time is very faster in HDFS file system team. Reading time is very faster in HDFS file system. Reading time is slower in normal file system. If data is less, reading is faster in normal file system. If data size is bigger, then reading time is slow. Reading time is slow team. Clear, right? Clear, right, team? So I recommend all of you to download data sets from this location. Sorry, team. I recommend all of you to set up a virtual machine by purchasing this course. Team, Apache Hadoop and Spark virtual machine. So this is the virtual machine. By purchasing this course, this is completely free. Purchase this course, set up Apache Hadoop and Spark virtual machine, download this data sets, click on here, download this data sets. Then as part of our HDFS commands practice, we are going to see this data sets. We are going to use this data sets team. Okay, so clear, right, team? Yeah. Yeah. Now let's see what is replication and replication factor team. So we seen HDFS file system what is block, right? What is HDFS file system? What is block? Now let's understand what is replication and replication factor. Replication means duplicate copy team. Replication means duplicate copy. Replication means duplicate copy. Duplicate copy. So replication factor means how many duplicate copies. How many duplicate copies? How many duplicate copies is called replication factor. Replication factor. Okay. So the default replication factor, the default replication factor is 3. Default replication factor is 3. We can increase or we can decrease. We can increase or decrease. We can increase or decrease based on our requirement. Let's say our hardware is normal hardware. Our hardware is normal hardware. Failure chances are high compared to certified hardware. So to resolve that failures, we will take multiple blocks. Instead of 3, let's say I am taking 5 blocks. If one mission down, I have 4 missions to take request and process. So we can increase, decrease based on our requirement. By default is replication factor is 3. So we can increase or decrease based on our requirement. When we go for decreasing replication factor, let's say team, my hardware is trusted hardware or certified hardware. Then failure chances are very less compared to normal hardware. Then instead of maintaining 3 copies, I will maintain only 2 copies. If one mission down, I have another copy. Very rare cases, our hardware may fail. So we can decrease also thing. We can increase or we can decrease. Okay. So let me explain to you how to increase and how to decrease. In HDFS-site.xml file, we have replication. Let's check. So DFS.replication. This is the option thing. This is the option. So DFS.replication. So where we change this one? Inside HDFS-site.xml. Inside HDFS-site.xml. Here we take one property. In this property, we take a DFS.replication. DFS.replication. Here we can increase or decrease it. Default is 3. If you not configure any value here, means default is 3. Okay. So we can increase or decrease based on our requirement inside HDFS-site.xml thing. So we can change the replication value. We can change replication value in HDFS-site.xml file. HDFS-site.xml file thing. We can increase or we can decrease based on our requirement. Clear, right? What is replication? And what is the replication factor? Replication means duplicate copy team. Replication factor means how many duplicate copies you want to keep in your system. How many duplicate copies of each block? How many duplicate copies of each block? Copies of each block is called replication factor. Okay. So clear, right? Yeah. Yes. Now let's see under replication. When we get under replication situation. So under replication means if any mission down, if any mission down, then the blocks under that mission comes to under replication. First point, if any mission down, maybe the reason with network issue or hardware issue or operating system issue or some other issue. So due to issue, one mission is down, one or multiple missions are down. The blocks presented in that mission comes to under replication team. Let me see. So here, let's say team here, this mission is down team. This mission is down. This mission is down team. Then what NameNode do? So NameNode will not get any heartbeat signal from this mission. Yes or no? NameNode will not get any heartbeat signal from DataNode 3. So every DataNode sends heartbeat signal. How NameNode knows about how NameNode knows about failed missions. Every mission team, every mission sends heartbeat signal. Every DataNode sends heartbeat signal. Let me check here. Control F, heartbeat interval. So this is the heartbeat interval team. So this is heartbeat interval. Heartbeat interval is every 3 seconds. We can increase or we can decrease, depends upon our requirement. Every 3 seconds, DataNode sends heartbeat signal. If DataNode not receives, if NameNode not receives heartbeat signal from DataNode, any of the DataNode, then it marks that mission as down. So whenever it marks that mission, whenever it identifies mission is down, then if any mission down, the blocks under that mission comes to under replication team. Under replication. what will happen? What will happens in under replication situation? Under replication situation. Under replication situation team. What will happen under replication situation? So under replicated blocks means blocks less than or equal to blocks less than replication factor. Blocks less than replication factor. We can say under replicated blocks. Blocks which are less than replication factor. Blocks with less than replication factor is called under replicated blocks. So whenever under replicated blocks comes, it will prepare, NameNode prepares under replicated blocks file. NameNode prepares what NameNode do? NameNode prepares under replication, under replicated blocks, under replicated blocks. It will prepare a file team. In this file, it will maintain all under replicated blocks team. All under replicated blocks. So here it maintains block 1, comma block 3. These are under replicated blocks. Block 1 and block 3 under replicated blocks. What it will do? NameNode asks other missions to create or ask other missions to create under replicated blocks, to create under replicated blocks. So it will ask all the missions. Let's say this mission accepted to replicate block 1. This mission accepted to replicate block 1. Okay. This mission accepted to replicate block 1. This mission accepted to replicate block 3. Then here team, here it will change DataNode 3 to DataNode 2. Coming to block 3, it will change DataNode 3 to DataNode 1. So this complete process is called under replication. Under replication team. Under replication. Under replication means blocks less than replication factor. Blocks less than replication factor is called under replication. Blocks less than replication factor is called under replication. If NameNode gets under replication, it will prepare file and it will ask other DataNode missions to replicate. If data nodes are accepted or replicated, it will modify metadata. It will update metadata team. If data nodes are replicated, if data nodes replicated, if data nodes replicated, then NameNode updates metadata team. Clear, right? So what is over replication, sorry, under replication? Team, did you understand under replication situation? If it is in under replication, name node maintains one file and identifies what are blocks presented in file missions, and it will prepare one file, and it will ask other missions to replicate that failed under replicated blocks team. So in cluster, any one mission, any mission may accept request to replicate blocks. Once blocks are replicated, new blocks information it will update in metadata file team. Metadata. Clear, right? Okay. Yeah. Now let's understand over replication team. So let's say team, here we have under replication situation. In under replication situation, one mission is down team. One mission is down. Okay. So what it will do? Let's say after some time, after some time, after some time, failed nodes become failed mission. After some time, failed mission issue is resolved. Issue is resolved, and it become up. It become up. It become up. So maybe network administrator resolved network issue, or hardware admin resolved hardware issue, or operating system admin resolved operating system issue, or any like electrical person or some other people resolved issue. Then after the issue is resolved, failed mission become up. Once failed mission become up, then it starts sending heartbeat signal. It starts sending heartbeat signal to its master called NameNode. Let's say this data node become up. So this data node issue got resolved. This data node issue got resolved team. Let's say this data node issue is resolved. This data node issue is resolved team. Issue is resolved. Whenever it resolved, it starts sending, let's say here, this one replace with second one. We have this one, we have a first mission. Yes or no? This one is first mission. Yes or no? So this is our data. So issue got resolved. Here we have a block B1. Here we have a block B3. Yes or no? Once issue got resolved, this one says, a name node, I am active, I have block 1 and block 3. So when it sends heartbeat signal to name node verifies metadata, then identifies newly, sorry, then it identifies these blocks are these blocks are over replicated blocks. Over replicated blocks. Over replicated block setting. So what this data node says? What this data node says? A NameNode mission. It sends heartbeat signal saying. It sends the heartbeat signal saying, a NameNode, I am active. I am active. I am having block 1, block 3. It sends that information to NameNode. Then when it gets that information, when NameNode gets that information, NameNode verifies metadata. Metadata, block 1 already with 3 replication factor. Block 3 already 3 replication factor. Block 1 already 3 replication factor, and block 3 already met 3 replication factor. Then it will prepare a over replicated file and places block 1, comma block 3. Block 1, comma block 3 as over replicated block setting. Block 1, comma block 3, then it identifies over replicated blocks. So these are over replicated blocks. Over replicated blocks. Block 1 and block 3, it identifies over replicated blocks. Then it will ask, then NameNode will ask, then NameNode will ask, NameNode will ask DataNode missions to remove block 1, comma block 3. So block 1 we have, currently block 1 we have in first mission, second mission, third mission, and fifth mission. Block 1 we have third mission, second mission, first mission, third mission. Let me take. See, block 1, first mission, second mission, third mission, and fifth mission. First mission, second mission, third mission, and fifth mission. Block 3. Block 3. We have block 3 we have in first mission, third mission, fourth mission, fifth mission. First mission, third mission, fourth mission, fifth mission. So block 1, block 3 greater than replication factor. Okay. So if any blocks greater than replication factor is called over replicated blocks. The blocks which are greater than replication factor is called over replicated blocks. Here block 1 greater than 3, block 3 greater than 3. We are using default is 3. So these block 1, block 3 greater than replication factor. Then block 1, block 3 called as over replicated blocks. What will happen? What will happens in over replicated block setting? In over replicated blocks. What will happen in over replicated blocks? NameNode asks data nodes, NameNode asks data nodes to to remove over replicated blocks. Any mission may accept any mission which has over replicated blocks. Any mission which has over replicated blocks may accept and removes. Okay, let's say team. So this mission is accepted team. Let's say this mission is accepted to remove block 1. This mission is accepted to remove block 1. Okay, so next one team, this mission is accepted to remove block 1. Let's say block 3. Then NameNode updates that metadata information. So from DataNode to it will remove block 1. So DataNode 3 has block 1. Next one, DataNode 4 removed. DataNode 4 is removed. So here DataNode 4 is removed block. Then we have 3. DataNode 3 keep that block. Okay. So once DataNodes removes blocks, then NameNode updates metadata. NameNode updates metadata thing. So let me take this diagram. Over replicated blocks. So clear, right team? What are over replicated blocks? What will happen in over replicated blocks situation? What happens in over replicated blocks situation? Clear, right? Yes or no? Yeah. Yes, team. So that's it for over replication team. Over replication. Okay. Yeah. Yeah. Now let's see HDFS write flow team. Let's diagrammatically discuss team. Let's diagrammatically discuss. When client want to write data, when client wants to write data into HDFS file system. When client want to write data into HDFS file system, write flow will happen in HDFS write flow will happen. HDFS write flow will happen in. Let's diagrammatically discuss team. We have a name node. We have a NameNode. We have a NameNode team. Let's say this is my NameNode. So we have DataNode. We have DataNode. We have DataNode team. So here we have DataNode. We have NameNode. We have DataNode. We have multiple data nodes team. We have multiple data nodes. Multiple data nodes team. We have multiple data nodes. So we have multiple data nodes team. Okay. So here client want to write the data into HDFS file system. So this is my client mission. This is my client mission. This is my client mission team. So client has a file. Client has a file. File name is file1. File name is file1. So client want to write data into HDFS file system. So file size is 300 MB. So file size is 300 MB team. Client want to write 300 MB data, 300 MB data into file system, Hadoop cluster. So this is client requirement. Client may execute HDFS command. Client may execute HDFS command to write data. Client may execute Hive query. Client may execute Spark program. Client may execute MapReduce program. It may be anything for writing data team. Client may execute any of this program to write data into HDFS file system team. Then first request to storage request goes to NameNode team. Storage request goes to NameNode. Storage request goes to NameNode team. When client want to store the data, this storage request goes to client mission team. Client mission request goes to NameNode. What NameNode do? NameNode prepares metadata team. NameNode prepares metadata. It prepares metadata. It prepares metadata. In this metadata, as per our previous discussion, it based on block size, based on replication factor, based on proximity algorithm, it will identify data nodes and divides the file into multiple blocks and prepares metadata. Let's say it says file 1, block 1, store 1, 3, 5, file 1, block 2, store 2, 4, 6, file 1, block 3, store 3, 4, 5. Let's say it prepared this metadata. It sent this metadata back to whom? Client. Client will receive response to team. First, client will send request a NameNode. I want to store. This is first request. Then what NameNode is doing? NameNode is preparing metadata. NameNode is preparing metadata. It's preparing metadata, returning metadata to client. NameNode is not responsible to write the data type. NameNode prepares the metadata. NameNode prepares the metadata and returns metadata back to client. Saying client, this is the metadata you can use for your stories. Then once it got metadata information back, then client performs HDFS write flow team. Client performs HDFS write flow. Client performs HDFS write flow team. Here we have two important points. We have a data queue. We have data queue. We have acknowledgement queue. We have data queue and we have acknowledgement queue team. So data queue, this is data queue, So this one is acknowledgement queue. Data queue and acknowledgement queue team. Here it will store first block 1 details. First it will store block 1 details. This is block 1. So it will store block 1 packets team. It will store block 1 packets into data queue. Block 1 packets. It will store block 1 packets. So same way for block 1 we have different packets. It will create block 1 packets into data queue, acknowledgement queue. It will prepare blocks, data queue and acknowledgement queue. In data queue it will maintain blocks, packets. Acknowledgement queue it maintain packets, and it will prepare data pipeline. So data pipeline for block 1. So it requires 1, 3, 5. 1, 3, 5. So it will prepare in this way. 1, 3, and 5. So this is called pipeline, data pipeline, data pipeline, data pipeline tip. It will create a pipeline. In this way, it will create a pipeline tip. It will create a pipeline. Pipeline. Then in this pipeline, client is responsible to write data into first data node mission. First data node mission means this is sorting order returned by name node. In this way, in this list, in the first one, client is responsible to write data into block. Client is responsible to write block 1. Okay. So here in this block 1, data moves from this data queue to block. This data queue to block. This data queue to block. This data queue packet to block team. In this way, data moves team in HDFS write flow. In HDFS write flow, from data queue to block, data moves team. If anything failed, let's say this block is failed. If block is failed, if any block is failed, same thing it will get from acknowledgement queue team. It will get from acknowledgement queue, and again it will try to write data into block. If everything is successful, each packet it will mark as completed. Mark as completed in acknowledgement queue. It will says mark. It will mark as success stream. If all packets are successful, if all packets are successful, if all packets are successful, block 1 is completed. Once block 1 is completed, remaining data nodes, data node 3, data node 5, through this pipeline, they replicate automatically. These data node 3, data node 3, data node 5 replicates blocks automatically through this pipeline. Once block 1 is successfully written into data node 1, remaining data nodes communicate with the data node, and remaining data nodes communicate with the data node which has a block, then replicates into their missions. Replicates into their mission stream. This is called HDFS write flow. HDFS write flow. This entire process is called HDFS write flow too. HDFS write flow. Clear, writing? What is HDFS write flow? What is HDFS write flow? Clear, right? Okay. Yep. Yep. Next important one, HDFS read flow team. When client want to read data, when client wants to read data from HDFS file system. When client want to read data from HDFS file system, client may be HDFS command, client may be HDFS command, client may be MapReduce program, client may be MapReduce program, client may be Apache Pig, client may be Apache Scoop, client may be Apache Hive, client may be Apache Spark, client may be Apache Spark, client may be Apache Flink, client may be Apache Beam, client may be anything, any HDFS Hadoop client, any Hadoop client team, any Hadoop client, client may be any Hadoop client. They want to read data from HDFS file system. They want to read data from HDFS file system team. Then HDFS read flow happens team. HDFS read flow happens. Client says, let's set him. This is HDFS read flow. HDFS read flow. HDFS read flow team. So client want to read using any of this program. Client says read data. Let me here we have one more important mission team. any processing request, read request, any processing request or read request comes to, any processing request or read request comes to name one more important demand called resource manager team. One more important demand called resource manager. Resource manager team. Resource manager. So here we have DataNode plus node manager. Here we have DataNode plus node manager team. DataNode plus node manager. DataNode plus node manager. DataNode plus node manager. DataNode plus node manager. Okay. So DataNode plus node manager team. We have DataNode plus node manager. So here we have a blocks. Let's say we have block 1, block 1 and block 1. Block 1, block 1 and we have block 1 here. Block 1. Next one we have block 2. Block 2 and block 2. So this one is block 2. Block 2, block 2 and block 2 team. Block 2. Next one we have block 3. Under 3, 4 and 5th mission. And 5th mission we have block 3. Block 3, block 3 and block 3. We have in this way team. In this way, block 3. Then client requested, client says read file 1. This is the request. So read request, any processing request comes to resource manager team. Any processing request comes to resource manager. This is request. Then whenever it receives a request, first resource manager communicates with NameNode. A NameNode, I want to read data, file 1 data. I want to file 1 data locations. I want to file 1 data locations. Resource manager communicate with NameNode. NameNode reads metadata from here. Okay, reads the metadata from here, then returns this metadata information back to client. Returns this metadata information back to client team. It returns metadata here. It returns metadata. So this is fourth step. It will return metadata team. It will return metadata. It will return metadata to resource manager. It will return metadata to resource manager. Fourth step is it will return metadata to resource manager. If it is processing, then client program, you request resource manager. So client program request resource manager. Okay. So here, let's say team. So here, through the resource manager team, client will get this data. Client will get this data team. Client will get this data. Client will get this data team. Once a client will get this data, client will start performing HDFS read flow team. HDFS read flow. So client will perform HDFS read flow team. Fifth step, client will perform HDFS read flow. HDFS read flow team. So first client start reading block 1 from first mission, block 1 from first mission, block 2 from second mission, block 3 from third mission, block 3 from third mission. This is parallel reading team. Parallel reading. It reads data. It reads data. First block from DataNode 1, second block from DataNode 2, third block from DataNode 3. Parallel reading, parallel processing. So it reads block 1. It reads block 2. It reads block 3 parallelly from 3 missions. That's why reading is very faster compared to other technologies. In HDFS file system, data is distributed. In HDFS file system, data is distributed. So response we will get very faster team. Response we will get very faster. Okay. So based on the sorted order, NameNode returned information, client will start reading data from corresponding missions team. Corresponding missions. So this is HDFS read flow team. HDFS read flow. In HDFS read flow, client will send a request to NameNode. If it is HDFS command, directly it will reach to NameNode. If it is MapReduce, if it is Spark, Hive, Scoop, through the resource manager, request reaches to NameNode. NameNode identifies metadata of that requested file, returns that metadata to client mission. Once a client receives metadata in a sorted order, each block with sorted order. Assume DataNode 1 in Hyderabad, DataNode 2 is Hyderabad, DataNode 3 is Hyderabad, DataNode 3, 4 and 5 is Bangalore, 6th one is Chennai. Client is requesting from Hyderabad. For client which is nearest one, 1, 2, 3. Then NameNode prepares metadata, returns metadata nearest data blocks to client mission team. Nearest data blocks to client mission. That is very important team. So based on the sorted order returned by NameNode, client will start reading data from corresponding missions. It will not read block 1 from 1, 3, 5. It will try to read data from block 1 from DataNode 1. If DataNode 1 is busy, it will go to DataNode 3. If DataNode 3 is busy, it goes to DataNode 5. So in this way, it will give priorities team. In this way, it will give priorities. Okay. Clear, right team? HDFS read flow. We already understand the HDFS write flow. HDFS write flow. And this one is HDFS read flow team. Okay. Clear, right? Okay.